All right. Next up we have Nico from Arcium. They actually just rebranded, and they're building an MPC compute network to basically run private confidential computations on a network of nodes without actually revealing any of the information, and you can actually do computations between different nodes. And he's going to tell us a little bit more about some of the multi-party computation protocols that they're also using. Yeah, give it up for Nico.
As introduced, my name is Nico. I work at Arcium. This talk is, I think, a little bit broader than you let on. It's more generally about if we have the goal of wanting to achieve confidential computing. So, we have encrypted data. We want to be able to compute directly on that encrypted data without anyone being able to decrypt it or needing to decrypt it. What different technologies and cryptographic primitives and whatnot exist, sort of what the trade-offs between those look like. But first, I think it's important that we define, DCC, decentralized confidential computing. I assume most people in the room probably agree that this is something that's important to have, but if not, please debate me. We believe that without private computations on blockchains, a lot of things aren't really feasible, or at least not feasible at the same scale as traditional finance. And so for that reason, we want to have that. So the desired properties of that are, obviously, we want to have it be trustless. So that means we don't want a system where it's like, hey, I'm the centralized party. Everyone give your data to me, and I promise you guys I won't mishandle it, but I won't leak it to anyone. Second, we want autonomous execution. So concretely what that means is we want computations over encrypted data to be executable in a similar manner as smart contracts, meaning we can have pretty much any trigger. We don't need to have some interactive protocol or something like this. Next, we want to have fast performance. Logically, who doesn't? That pretty much sums it up for what we think is important. So in terms of that, the first technology is logically trust execution environments, which I'll just learn a bit about as well from the previous talk. So I don't think we need to re-explain how it works or what it is. However, we think that in terms like how you presented it, where it's defense in depth, for example, or where you have many systems or whatnot that work together, it is sensible. However, we think as the key primitive that you rely on for confidential compute, it's not necessarily the best technology, because although you have things like remote attestation that proves execution, or separated hardware that allows you to, in theory, compute on data without leaking it to the rest of the system, in practice, unfortunately, this hasn't. This hasn't always been the case. If you look up the Wikipedia page of Intel SGX, you will see quite a few exploits on that, unfortunately. And if you look at systems that have previously attempted to build decentralized confidential compute, such as Secret Network, that didn't end up all too well, because if you rely on that without any other cryptographic primitives, what essentially happens is that as long as you don't have it only ran by permissioned operators, or only ran in places where you yourself can make sure that that hardware isn't tampered with, at some point someone will find a side channel or use an electron microscope in some new manner and find a way to extract private data from your TEE. So for that reason, we think for the case of decentralized confidential compute, where you really want to have a network where anyone's able to participate to compute confidential functions, TEEs, at least by themselves, aren't sufficient. So the next solution, I'm sure many of you are familiar with as well, zero-knowledge proofs. In theory, seem like a step up in this form, right? Because they're provably secure, or at least somewhat provably secure, in that you can reduce them to some basic cryptographic assumptions, rather than having to trust that the hardware is correctly implemented or doesn't have any vulnerabilities in it. However, they have some downsides for the case of privacy as well, in the form of that you can't have efficient shared state in them. And what I mean concretely by this is that, as most of you know, the main idea behind a zero-knowledge proof is that you basically say, okay, I have some data that's secret and hidden from the world and whatnot, and now I want to disclose to you so that we can compute on part of this data, a piece of this data, and I can prove to you that this piece of the data fits the hidden data initially. So So this sounds great, but in most cases, on-chain, in most cases, you have shared state. So that means if you consider an order book, for example, you have the case that you say, I, Nico, I submit an order into the order book where I say I want to buy something, I have it encrypted or otherwise obfuscated, and you have a second party that also submits an order into this order book. Now, in theory, if you want to use zero-knowledge proofs in this case, what you would need is you would need someone to be able to see the plain text of your order and the other person's order, and essentially be able to then generate a proof where they say, hey, I show that these orders match. Problem is, if we want to keep it decentralized, I can't see the other person's order, and the other person can't see my order either. And you could say, for small systems, we could set up a system where we communicate with one another and generate the proof that way. But if you imagine an order book with thousands of users, for example, then you'd need a case where you have thousands of people coming together to generate a zero-knowledge proof. So this isn't necessarily feasible either in the case of decentralized confidential compute. The next example is, I think, takes a step up on that once more, which is fully homomorphic encryption. Which, again, the idea here is that you define a special type of scheme, encryption scheme, whereby you have addition and multiplication homomorphic over it. So in other words, if I take value x, I encrypt value x, and then I want to add 3 to that value, or I want to multiply it with 5, using fully homomorphic encryption, I can do that directly on the ciphertext, and the result will be the same as if I had added or multiplied to my value x initially, and then encrypted it. So in the case of the order book example I gave before, this essentially allows us to realize what we couldn't before. We have the order book, we have all our orders, and then we just implement a matching algorithm on the ciphertext directly without needing to decrypt them. And since we can support addition and multiplication, you can look this up on the internet, or you probably already know it. Using addition and multiplication, you can define pretty much any algorithm using these basic building blocks. So this sounds great again. However, in practice, today at least, it still has quite a few limitations. So the first one in the form of extreme slowdowns. So many algorithms nowadays are significantly slower in the case of multiple orders of magnitude as compared to plain text when you implement them using fully homomorphic encryption. No selective disclosure. So concretely, what I mean by this is that out of the box, most FHE algorithms, or basically any FHE algorithm that I know, doesn't really allow you to write algorithms where you say, okay, I have a bunch of ciphertext, or I have some huge value that's encrypted, and I only want to output part of it as a plain text or something. Pure FHE doesn't really let you do that in a simple manner. Next, you have no out-of-the-box verifiability either. So that means if you have FHE, you have some ciphertext, and you hand it off to someone, and you tell them, hey, please compute this function on the ciphertext for me. There isn't really a straightforward way today, at least, that the other person can actually prove to you that they didn't just do some random algorithm on it or did anything at all in the first place. So, for those reasons, what we ended up going with Arcium is MPC with semi-homomorphic encryption, or in other words, it's just a more complicated way to say additive secret sharing, where the idea basically is that we implement MPC and use that to do obfuscated operations. So, quick recap, multi-party computation, the main idea is that you have n what are called players, or parties sometimes, and you essentially, again, like in other cases, have some value x that you want to keep secret, and then the question is, instead of encrypting it, or hashing it in the case of DK, in this case you do something called secret shares. And secret shares basically just means you take x, and you have some algorithm to transform that into this representation here, which is called secret shares of x, meaning each of the n players gets their own little share of x, and if you combine a certain threshold of those x back together, you get your original x value back. And the important characteristic here is that each of those x shares doesn't leak any information about x itself. And the cool thing about additive secret shares is that they're homomorphic in respect to one operation. You might have guessed it by the name, which is addition. However, they are, okay, this is the wrong text, but multiplication still has a bit of overhead inside of it. And the main overhead, we'll look at the math in a second to get a bit more of an idea of why that is. But the main overhead is basically scalability with number of players, because multiplication basically requires you to communicate between players, which then again plays into the trust model, because if it's essentially more expensive to have a whole bunch of people communicating together, that means that honest majority or Byzantine fault tolerance, like most blockchains today have, might not necessarily be good enough, because 51% assumption is fine if you have 1,000 nodes, but probably not as fine if you only have 10 nodes or so. But yeah, so let's go over a quick example of how MPC or additive secret shares actually work. So let's say a super simple example. Alice, Bob, and Charlie all have their salary, ABC, and they essentially want to compute what is the average of our salaries. And yeah, what they basically do is they take each of their salaries, transform it into secret shares with the property that if you add those shares up, they give you the initial salary back. So we take A, we do A1, A2, A3, and then if you add those back up, you get A, and you do the same thing for B and C. Then you take one of these secret shares and distribute it to each of the players. And each of the players can locally compute A1 plus B1 plus C1, and this should be here, and divide that by 3 as well. And the cool thing about that is that at the end, they get a bunch of shares of what the average is, and if they add those back up together, yeah, they're able to compute the average without ever leaking what the actual salaries are to one another, which is pretty nice. And I think what's important to mention about this example as well is what you notice here is that this is very efficient if you compare it to plain text. So the players only ever have to do additions on their local computers, so that's super fast. And they have to do divisions by constants on their local computers, which is pretty fast as well. And yeah, and that basically shows that if we have additions, constant additions, and constant multiplication, those are all super fast. But by the way I've written it here, you might notice I'm leaving one out, which is multiplication, which is sort of the big bad of MPC. And to see why that is, let's quickly take a look at an example. Yep, nice. So the thing with multiplication in the case of MPC is that you usually do it with this little trick here, using something called Beaver triples. And the idea here is just that you have these two secret share values, A and B, that no one knows, that you generate up front, that equal some C. And then basically you can run this algorithm here where you say, D equals X minus A and E equals 1 minus B, reveal D and E to all parties, and then you can basically add these up like this at the bottom, and get your X, Y at the end. However, the important part here, is this specific part here. Differences D and E are revealed. And the reason that this is important is because every other operation here is locally executed on the computer, and it's just a couple of additions and stuff like that, so not very hard. But reveal basically means that you need to have all the parties inside of your player network communicate with one another to add all their shares up, and that's generally what makes it slow. And if you basically notice here that this is the algorithm that's necessary to do multiplication, that means that if you approach naively at least, every single time you do a multiplication, you need to do one of these reveal steps, which in turn then means that, you have an O of n squared operation each time, which isn't great. However, the thing that you can do to circumvent this to some extent is something called packed secret sharing. And the idea here is basically really that you just say, since the important part is that if you have independent multiplications, you can basically just put them all in a vector and do the communication rounds for those all in parallel without needing to do it for each individually, which then drops your communication cost from O of n to O of 1. And in addition to that, most modern hardware has pretty decent hardware acceleration for vector operations, so you can take advantage of that as well along some other optimizations. And FHE can find use in MPC as well, so you can use it in the pre-processing, which generates those Beaver triples at the beginning. However, we found in our case that OT is actually, or offers better performance than FHE does in the case of the first step of generating those Beaver triples you need for multiplication. And to round it up, let me just give a quick overview of what Arcium concretely does. So, Arcium is basically just a computation network that allows us to run multi-party computations. Inside of it, we support mainly two schemes, Bidoza and Manticore. Speed is kind of similar to Bidoza, so not as important. And the cool thing here is, Bidoza basically is this super secure, dishonest majority trust assumption scheme, which allows you to do things pretty efficiently. Manticore on the flip side is one that is honest majority assumption, but then allows you to do a bunch of optimizations and be very fast. Outside of that, some more stuff here, but that's pretty much it. So, thanks for listening.
Okay.
Yep. I see your question.
Thanks for your talk. But I wonder how to implement SHE, semi-homomorphic encryption. Is there any reference to any publications for focusing on SHE?
Yeah, for sure. So I think like the naming is probably what makes it a little bit confusing, right? Because fully homomorphic encryption generally means you say multiplication and addition can be homomorphically done on obfuscated values. Semi-homomorphic encryption just means one or the other is possible directly, right? And the idea in our case is just that we say,
it's
just that we say that addition here, just that we say that addition can be done directly on obfuscated values without needing any extra steps or anything. That's why I quickly mentioned at the beginning. Maybe a less confusing name would be additive secret sharing, because that's a bit more famous name than calling it SHE.
So you mean that only addition is homomorphic, but multiplication is not?
So addition is homomorphic directly, and for multiplication you need that extra algorithm I mentioned before that can be parallelized to speed it up.
Okay, I got. Thanks a lot.
Any other questions?
Hi, and thanks for the talk. Just a very general perspective question. You mentioned a bunch of different encryption technologies that all create a type of proofs. And then let's say, also the question was interesting, if you have application use cases that use your system right now, would be curious. That's one question.
Yeah.
And the second one, if I'm an app developer and I need to use a mix of proofs for my application, so I can't just use only CK or FHE, or I need a little bit of everything, how do you envision this space in general for an app to use different kinds, a mix of proofs? I'm just curious if you have an opinion on it.
Yeah, for sure. So, sorry. Okay, yes, I didn't want to interrupt you. So for the first part, in terms of like, so we are in testnet right now, and most apps are being built on top of us. So more generally about like the company and the technology is basically we offer an MPC coprocessor for existing blockchains, right? And so that basically means you can have encrypted data living on Solana, Ethereum, what have you. We can basically then delegate computations to the network to execute, and then basically get back. It gets computed with MPC, and you get back the result plus some proof of correct execution. And so in terms of that, most applications are being built over there on testnet, at least right now. It's mostly DeFi-related stuff, where people are building trading or building lending or something like this with basically encrypted values for who's trading how much and things like this. With regards to how I see like different technologies or different primitives playing together to build the ideal system. So, obviously I'm a little biased in this sense, but I think for like general confidential compute, so generally speaking, computing on encrypted data, MPC, at least at the moment, is the best way to go. That's what we're building with it. However, you can always do better, right? So in terms of, for example, I mentioned quickly before that you get a proof back where it says that it was actually correctly executed. For that, ZK is a logical choice, especially because I don't think there's any other direct methods for that. So I think ZK is great for proof of execution, not as great as other stuff for privacy specifically. And on top of that, I think TEs are awesome as well. not for necessarily privacy, like as a first-class citizen in terms of providing privacy, but as a defense-in-depth mechanism for pretty much any system, allowing you to, have that little bit of extra defense in case your cryptographic implementation has a bug or something. You can be sure that if it's running instead of a TEE, it will be a bit harder to exploit at least. So yeah, I don't know if that answers your question, but
Yeah, thanks.
Quick question to the Arcium network. Can you maybe switch to the slides with the ESOP and Manticore?
yeah.
You said there's ESOP, I think, has a dishonest majority resistance.
Yep.
But what's the speed difference factor between Manticore and DDoS?
It's quite significant. It's like 100x or something like that. But I think it's also important to envision like the different use cases in this case, right? Because essentially, when you're going to be using DDoS, or DDoSa, generally speaking, it's like if you're doing some DeFi thing or something where you're managing a bunch of money, let's say. However, in those cases, oftentimes the actual computation that you're executing isn't going to be super computationally heavy. Basically, it's going to be like, oh, you have, for example, an order book and you have a matching algorithm, but usually if you look at blockchains in general, usually order books already have a max size or something like this, right? So in terms of that, I think it's quite akin to how blockchain programming works today and being like a bit constrained. Manticore on the other side is for sort of the other end of the spectrum. It's for like cases where you say, okay, I have some massive amount of data. I want to compute encrypted on it, but I can have a bit better trust assumptions. So an example for this is biggest buzzword ever, but AI. So saying you have a couple different parties that want to train a model together. Using Arcium, basically, they can have a very easy out-of-the-box way to organize and compute, for example, training on an AI model in a somewhat reasonable time as opposed to doing it in plain text.
So you combine these two, and how do you decide which one to execute or to use? This is a user-developer decision.
This is developer decision. So basically, we provide tooling that allows you to write essentially as close as possible to pure Rust or a higher level language, which we then compile down to an intermediary form, and then basically similar to, for example, More, you can then choose, instead of a proving backend, you can choose an MPC backend. So you can then say, oh, I want this to run on DDoS, or I want this to run on Manticore. Yeah.
Okay, got it. Thank you.
Yeah, no problem.
I think there was one more question in front.
So, first of all, I want to say that I totally agree with, partially agree, let's say, with the issues of on these SGX.fail is where you can find the list of exploits. But one issue that what I want to say is that I do agree that we need to take care. But one issue that I have is that somehow we seem to forget that all our computation runs on some hardware. So it's not just these that are vulnerable to side channel attacks, right? Like, what are your thoughts about? Like, as long as you need the plain text somewhere, like, how do you make sure that it's secure from side channel attacks?
Yeah, for sure. So, in our case, that's the idea behind using MPC, for example, that you essentially you don't have this problem of having the plain text anywhere. You only ever have secret shares anywhere, and the only way that you can get the plain text from that is by essentially, depending on if you're using Manticore or DDoSa, by having 51% or 100% of all nodes colluding back together. So I think maybe I didn't, what I meant specifically about TEEs not being sufficient by themselves for private applications is that, of course, other hardware also is vulnerable to side channel attacks and other types of attacks. But usually, when you're building encrypted applications with encrypted data, you don't rely on the other hardware, not being broken. You rely on cryptography. For example, if you have a database in traditional computing, you wouldn't store you shouldn't store user passwords without hashing them, for example, inside the database, just because you'd say, okay, even though I don't want people to break into my database, I don't want my only recourse to be my implementation and potentially the database hardware. Instead, I add this extra thing on top where I assume that hash functions aren't broken. So because of that, I rely more on that than I do in traditional hardware. It's the same idea here, where we basically say we want to use cryptography to build systems where we rely on cryptography first and foremost, and potentially TEEs as defense in depth. but not systems where you rely only on TEEs for providing privacy. Does that make sense? Yeah, for sure, for sure.
You mentioned AI as a potential use case. There was another talk just now from another colleague of yours, and he was mentioning that there might be some communication overheads that limit perhaps the size of models and the complexity of the models. Can you speak a little bit to how far does it go and how far can it be pushed potentially in the future?
Yeah, for sure. So, whenever you're going to be doing anything on non-plain text, whether that's with MPC, whether that's with basically any cryptographic primitive, you're always going to have some overhead, right? However, what's quite cool about AI models, or at least what's quite fitting between like MPC and AI models specifically, is that in AI models, like generally speaking, depending on the training algorithm, you can parallelize a lot of the multiplications. And in like traditional, if you're computing on plain text, might not necessarily, this is why GPUs work so well. But this same principle basically transfers to MPC as well, because in MPC, additions are pretty much the same as just additions on plain text, so you can view them as basically free. But multiplications are a thing that's expensive, but not actually because of the multiplication in itself, but actually because of the communication overhead involved for each individual multiplication. But what makes that cool is that the most common thing is like matrix multiplication. In matrix multiplication, like essentially what you can do is you can take two matrices that are both secret shared, and you can essentially batch them all together. I quickly mentioned this before. And essentially only do one round of communication just with a bit more data. And that essentially means that, of course, you can't be as fast as plain text, but in terms of being like computing unencrypted data, I don't really think there's a better suited technology for AI training than MPC, simply for this benefit, that you get additions for free, and you get multiplications constrained by sort of the same way that the GPUs take advantage of them. So for that reason, you can take advantage of GPUs as well. So that was a little bit, a lot of thoughts at once. Let me know if that made sense.
So, do you see a future, did I understand correctly, that you see a future that maybe one day we're actually not going to be relying on GPU farms anymore, we could actually be doing all of the AI inference in MPC type environments? Like, do you think you could actually get to that point?
No, definitely not. And the reason is that MPC allows you to get confidential compute on AI. So concretely, that means it allows you to take not encrypted but obfuscated data where no one knows what that data actually is and compute with it, right? That doesn't affect performance. It only makes it worse to some extent. But what I more so meant is that the nice thing about MPC is that you can take advantage of GPU farms in this sense, because you can say, for multiplications, since additions are basically free and multiplications only overhead is round of communication, but that's decently nicely parallelizable, you can make MPC work pretty well for AI with not too much overhead and take advantage of GPUs as well.
So sorry to keep.
No, for sure.
So if you come in as a node on the network, do you come in with the GPU? So you log in as a GPU node on the network, or do you come in as a CPU node? How do you take advantage of the GPU in this process?
Yeah, so so that's what I went before. Someone else asked about like what use cases are most common at the moment. At the moment, the most common use cases are like DeFi-based stuff, which is because so far we support Doza. Manticore, we have like the cryptographic implementation, but we haven't implemented on Arcium just yet. So for that reason, for now, GPUs don't really make sense, because you don't really need GPUs for like non-AI stuff, at least when it's blockchain finance related. But yeah, in the future, probably will allow GPU nodes as well.
What is future here? How many years are that?
What's that?
How long of a future? Is it next year? Is it 10 years?
Yeah, 20 years.
20 years?
Just kidding. Probably within 6 months.
6 months? Okay, that's good. Thank you very much.
Yeah, no problem.
So your colleague was talking also about like the potential use cases for AI, and he said that at the moment it's possible to do it with some regression, for example. But when we are talking like about the really interesting stuff, like building big deep learning models, when will it be possible to do like to build foundation models? For example, what I think is interesting for the use case of medicine, using this technology. So what do you think, how many years will it take to be at that point?
Hard to say, to be honest. Like, I mean, it always depends on the size of your model. Like you can compute anything on this technically, right? You could train LLM on this. It would just take forever, right? So in that case, it really depends on the size of the model, to be honest. Like you can do regression, XGBoost, like decently standardized stuff for non-LLM based models already today. However, I don't think, so basically, I think to answer that is, for Manticore specifically, I think we have a ton of optimizations in place already. And I think most interesting use cases with regards to medicine specifically, you can probably do within, you can probably already do, within 6 months or so. And the reason I say this is because oftentimes in medicine, you have the case that you want to train a model, and then if you're training your model, since medical processes and stuff like this are already so long, if your model takes like, a few days to train or a few weeks, in many cases doesn't make as big of a difference. So that's mostly what makes us bullish on it. But yeah.
Thank you.
Yep.
What about inference? You're talking about learning?
Sorry?
What about inference?
Inference?
Yeah, you just talking about learning. What about, I have a pre-trained model, I just want to run inference on it once. Is it already good, like a big foundational model?
I mean, inference is much cheaper than training, so yes.
That should be doable today.
Yeah.
Okay.
You mentioned the computation overhead for multiplications. Is this something that is like built into MPC, or is there hope that there may be like protocols that come over this challenge?
So as far as we know today, that's something that's fundamental to at least additive secret shared MPC. However, if you find a faster way to do it, you're going to be very famous. So, at the moment, this isn't implementation specific. This is just like an MPC thing in general.
Thank you.
Okay, I think with that we're at the end of time. Thank you very much, Nico. Give me a round of applause.